Dear students, this is lesson number 5, and today we will discuss proteolytic theory, and we will solve problems on buffer systems of first type. So, first of all, let's remind what is proteolytic theory. So, in proteolytic theory, all substances in solutions are divided into two main groups. One group is called proteolytic acids. Proteolytic acids can donate a proton. Another group is proteolytic base, and proteolytic bases can accept proton. So the first task is to find particles which can be a proteolytic acid. So let's consider it. Some of the particles have charge, and actually some of the particles can be ampholytes, so they can play both roles. They can be proteolytic acid and proteolytic base. So in that particular question, dihydrophosphate ion can donate a proton. It's a weak electrolyte. I draw two arrows here. This is arrow. And so the equilibrium will look like that: H plus HPO 2 minus. NH3, it is not proteolytic acid. It can not donate a proton. Water is ampholyte. It can both donate a proton and accept a proton. In that question, it is the proton donor, so it gives a proton. And hydroxide, HS minus, it is also proteolytic acid, H plus S 2 minus, and H2S also can be proteolytic acid, H plus H S minus. And the last substance, maybe it looks complicated, so this is organic compound. I will draw it structurally. There is a nitrogen. It has different substitutions, methyl here, and 4 protons, and it is positively charged. So basically you should know that valency for nitrogen is 3, and one bond here, it is called donor acceptor bond, and nitrogen has electronic pair and proton has empty s orbital, so electronic pair of nitrogen is placed on empty orbital of proton. Thus the donor acceptor bond is formed, and actually that proton can be donated, and the equilibrium will look like that: CH3 NH2 plus H2. And this substance will be called methylamine. The next question is to find proteolytic bases. I just told you about organic compounds containing nitrogen, that there is electronic pair, and this type of compounds can be proton acceptor, so I write here plus H plus, and the result is C6H5 NH3 plus. so it is proteolytic basis. OH hydroxide ion, of course, it is proteolytic base, plus H plus, and it forms water. Water itself can also accept a proton, because oxygen also has electronic pair. So it will form the substance called hydronium ion, H3O plus, hydronium ion. Ammonia ion, it is not proteolytic basis because all valences are used already, and the electronic pair of nitrogen already used for forming bond with protons, so I will cut it. And hydrosulfate ion also can accept a proton, and it will form sulfurous acid, H2SO3. Now we will solve problems on buffer systems of first type. You can stop the video and write down the problem. On the lecture number 5, I gave you the procedure for solving the problem on buffer systems, the algorithm. So the first part of that algorithm is to write down the components of the buffer system. So let's write down the components. So we have sodium dihydrogen phosphate, and we have disodium hydrogen phosphate. So on the left side we usually write more acidic components, so sodium dihydrogen phosphate, and disodium hydrogen phosphate. So the second step according to the our procedure is to show the state of substances in aqueous solution. So let's write that what happened with both substances. So let's write sodium dihydrogen phosphate. It is a strong electrolyte, so it dissociates fully. And A plus H2PO4 minus, here is minus, here is plus. So this is full dissociation, so there is one arrow. Another component, disodium hydrogen phosphate. It is also strong electrolyte, and it also dissociates fully to sodium ions plus HPO4, 2 minus. And here in phosphate buffer system, we also have to write the dissociation of dihydrogen phosphate ion. It is a weak electrolyte, so in some content it dissociates. Is it weak? We write two arrows, H plus plus HPO4, 2 minus. Basically, that equation show us roles of both substances as per proteolytic theory, we see that this ion will be proteolytic acid. It can donate a proton, and this is proteolytic base. So if we look on the system, we can say that that component is proteolytic acid, and that component is proteolytic base. Now we will calculate pH of our buffer system. So the basic formula for calculation of pH for first type buffer system is pH equal pKa plus logarithm number of moles of salt and number of moles of acid. So pKa, it is given here, it's 7.2, and the question is what is salt and what is acid in that terminology. So if we look on the composition of buffer solution, we see both salts, but we will consider that one salt is more acidic, so this will be acid in that terminology. I will put like this, and this will be salt. Let's find number of moles of salt. Number of moles of salt. Salt is that compound, disodium hydrogen phosphate. So we have 50 milliliters with 50 milliliters of solution with that concentration. So we can always find number of moles as molar concentration multiply volume. Molar concentration 0.03 and the volume 50 milliliters, but we have to convert it to liters, so I write 10 power negative 3, and we will get the number 0.0015 moles. Now let's find the number of moles of acid. It's the number of moles of that compound. It's equal as well as C multiply V, so the concentration 0.3, the volume is 100 milliliters, so we convert it to liters, it's 10 power minus 3, and we get 0.03 moles. Now we will write again pH equal pKa 7.2 plus decimal logarithm 0.0015 divided by 0.03. And if you do that calculation, you will get 5.9. This is pH of our buffer solution, of that particular composition. You should understand that pH of buffer solution depends on the composition. So if we change volumes of components or concentrations of components, we will get another buffer solution with another pH. The next part of our problem is to write the mechanism of the buffer action. So I remind you that buffer solution is a such solution that can keep almost constant pH after adding of strong electrolytes. We can add strong electrolytes of different types, but we consider only that electrolytes which can change pH somehow. So we divide strong electrolytes into two types, strong acids and strong bases. So I also call it external strong electrolytes. So the first situation when we add external strong acid. As example, we will consider HCl, hydrochloric acid. So if you add hydrochloric acid to water, it will fast change pH to acidic range. The water has pH 7, and the adding of HCl will move it to smaller numbers like 3, 2, 1, and even close to 0. But if you add HCl to butter solution, the pH will be changed very, very slightly. Why is that so? For that we have to write the mechanism. So HCl is a strong electrolyte, so in solution it dissociates fully. And these protons interact with water and form hydronium ions. Here should be two arrows, there is equilibrium. And these hydronium ions, we can consider it as proteolytic acid. So it will interact with proteolytic base in solution. Let's look here. What is proteolytic base here? That compound, disodium hydrogen phosphate, is proteolytic base. But disodium hydrogen phosphate exists in form of ions, so we will consider only hydrogen phosphate. Only that ion will interact with hydronium ion. So we write HCO plus HPO for 2 minus, 2 arrows, and it produces water plus the hydrogen phosphate. So, and let's write here the roles. So again, this is proteolytic acid, this is proteolytic base, and this will be called conjugated base. And here I put number 1, and here also number 1, because this is conjugated pair number 1. And this dihydrogen phosphate, it will be conjugated acid. And I put here number 2, and here also number 2. It is conjugated proteolytic pair number 2. And I also show here how the proton goes. Proton goes from here, from hydronium ion to hydrogen phosphate ion. The proton goes. Now we will write the mechanism of buffer action after adding strong base. Strong base. We will take as example sodium hydroxide, NaOH. So NaOH, it is a strong electrolyte. So in solution it exists in form of ions, sodium plus hydroxide ions. And this hydroxide ions is proteolytic base. So let's look on the buffer components. It can interact with proteolytic acid with sodium dihydrogen phosphate. Sodium dihydrogen phosphate exists also in form of ions, so we consider only dihydrogen phosphate ion. So let's write that OH minus plus H2PO4 minus, and it gives us water and hydrophosphate ion, which has a charge 2 minus. So let's write here the roles. This is proteolytic base, and this is conjugated acid. And here I put number 1, and this is proteolytic acid, number 2, and this is proteolytic base. No, sorry, it's conjugated base, number 2. And the proton goes from here to here for your better understanding. So this is the mechanism of buffer action. So the idea that strong base, that one, is replaced with a weak base, and weak base doesn't influence on pH that much as a strong base. The next question in comparison of buffer capacity by acid and buffer capacity by base. So to compare these buffer capacities, you don't have to calculate that. You just have to look attentively to buffer ratio and make a conclusion which compound in buffer composition we have more. Is it acid or salt? So number of moles of acid and number of moles of salt. We have to compare these two numbers. So let's read in our notes. We calculated number of moles of salt. So it was 0.0015, and number of moles of acid, it was 0.03. So we have more acidic component than salt component, and this component, it is proteolytic acid. It interacts with external strong proteolytic base. So here we write B, buffer capacity by external base, and here we write BA. It is buffer capacity by external acid, and we put the same sign here. So this is the conclusion. If we have that ratio of buffer components, we'll have that ratio of buffer capacities. Now we will solve another problem. Please write down that problem. You can stop the video. So first we start with writing of main components. So on the left side we usually write more acidic, on the right side less acidic component. So H2CO3 and NaHCO3. This is so-called acid. From electrolytic dissociation point of view, this is acid, and this is salt. From the point of view of proteolytic theory, this substance will be proteolytic acid, and this will be proteolytic base. Why? Let's write what happening with both substances in water solution. H2CO3, it is a weak electrolyte, so we write two arrows. It gives us proton, and it also produces hydrocarbonate ion and sodium hydrocarbonate. It's a strong electrolyte. I remind you that all salts are strong electrolytes. So in water solution there are no such molecules. There are just sodium cation and hydrocarbonate anion. So basically that particle, hydrocarbonate anion, can accept a proton. We see that it's here on that equilibrium. So this is proteolytic base. This is proteolytic acid. Now let's write the formula for determination of pH. pH is equal pKa plus logarithm number of moles of salt divided by number of moles of acid. And here I will put number 6.35. It is given plus logarithm. So salt is that substance, NaHCO3, and we know that there is 100 milliliters of solution with concentration 0.1 mole. So I write 100 milliliters, I convert it to liters, multiply 0.1. And below I will write the volume of acid, it's 50 milliliters. I will convert it to liters, 10 power minus 3, and multiply to the concentration 0.2. After you do the calculation, you will find out that actually the number of moles of salt and acid are equal. So you will get here 0.01 mole sorry, something goes wrong, and here also 0.01 mole. So actually it is a logarithm of 1, and decimal logarithm of 1 is 0. So the answer is that pH is 6.35. And there is also the question to compare buffer capacity by acid and buffer capacity by base. So if the number of moles of salt in buffer composition is equal to number of moles of acid buffer composition, it means that buffer capacity by acid equal to buffer capacity by base. And this is called hydrocarbonate or bicarbonate buffer, that buffer. So problem number 5, it is the same buffer. Please stop the video and write the problem. Okay, I'm writing the components again. More acidic component to the left, H2CO3, and less acidic here, NaHCO3. This is proteolytic acid, It's the same as in previous problem. This is proteolytic base. This is acid from terminology of electrolytic dissociation theory, and this is salt. And if you read attentively the task, you see that pH is already given, but we have to find volumes of each component. In your home task, while preparing for laboratory work number 3, you will do the same calculation. So first you have to write the formula for pH. pH equal pKa plus logarithm number of moles of salt divided by number of moles of acid. And we can write instead of number of moles of salt, we can always write concentration of salt multiply volume of salt, and below we write concentration of acid multiply volume of acid. So we see that this is given, it's 6.8, this is also given, it's 6.35. The concentrations of salt and acid are given as well. This concentration of salt and this is concentration of acid. And these volumes we have to find. And at the same time, there is that information that total volume is equal to 60 milliliters. So we can write volume of salt plus volume of acid is equal 60 milliliters. Or I will convert it to liters and write 60 multiplied 10 power minus 3 liters. Or we can also write 0.06 liters. Okay, so we can say that volume of salt is equal 0.06 minus volume of acid. And this is if we measure everything in liters. So let's put all the numbers inside the main formula. 6.8 is equal 6.35 plus logarithm. Now we will put concentration of salt. It's 0.2 multiply volume of salt, but I will put that 0.06 multiply volume of acid and divide by 0.1 because it's concentration of acid multiply volume of acid. So we see that only one unknown number in that equation, and this is volume of acid, and we will find it using our mathematical knowledges. So how we will do that? We will first remove that here. 6.8 minus 6.35, and it is a logarithm. And here I will cut, and here will be 2. 0.06 minus VA divided by VA. So this is 6.8 minus 6.35. It is 0.45, and it's equal to logarithm 2.006 multiply VA divided by VA. And now to remove this logarithm, we will do 10 power 0.45 is equal 2006 minus VA divided by VA. 10 power 0.45 is 2.818, but we'll round it and we write 2.8, and this is equal that number. Now I will move this here and I will write like that, and here I will open brackets and I will write 0.12 minus 2 VA, and now I will move that here, and it will give us 4.8 VA is equal 0.12, and VA is equal 0.12 divided by 4.8, and it's equal 0.025, and the units are liters or 25 milliliters. So the volume of acid in buffer composition is 25 milliliters. Is for that component 25 milliliters. And the volume of salt will be 60 milliliters minus 25. It will be 35 milliliters. So we have 35 milliliters here. Now we have to write the mechanism. So we will use again the same approach. So first let's write the mechanism when we add strong acid, HCl. So I do the same as I did in third problem. HCl is a strong electrolyte. It gives us protons which can influence on pH. So protons interact with water, forming hydronium ion. And this hydronium ion is proteolytic acid. So it will interact with proteolytic base. Proteolytic base is here. So proteolytic base, sodium hydrocarbonate, exists in form of ions. So we consider just hydrocarbonate ion. And we write the following equation. There is equilibrium, but it is moved to the right side. H2O plus H2CO3. So the proton goes from here to here. And let's name all the substances. It will be proteolytic acid number 1, and it is conjugated with conjugated base number 1, and it will be proteolytic base number 2, and this will be conjugated acid number 2. So once again, the idea of buffering action of mechanism, as we had strong acid HCl. HCl produces a lot of protons. These protons influence on pH, but we replace strong acid HCl with weak acid, with carbonic acid. This is a weak acid. It doesn't give a lot of protons, and pH doesn't change much. It changes just a little. So now let's write the mechanism when we add strong base. We take as example NaOH, and it dissociates and gives us sodium cations and hydroxide anions. This can influence on pH. So this is proteolytic base, and it will interact with proteolytic acid, which is H2CO3 OH- plus H2CO3. We write H2CO3 as a molecule because it basically exists in form of molecules. It is a weak electrolyte. So here again we got water and hydrocarbonate ion. So the proton goes from here to here. And let's name the compounds. This is proteolytic base number 1. And this will be conjugated acid number 1. So you see, water is amphiolite. In different situations, it can play a role of base, for example, as here, or role of acid, depending on the situation. And this is proteolytic acid number 2, and this is conjugated base number 2. And in that mechanism, we show that strong base NaOH that can influence on pH. It is replaced with weak base HCO3-. It is a weak base. And the last question, to compare buffer capacity by acid and buffer capacity by base. So to compare it, we have to compare the number of moles of salt. Salt neutralizes acid, strong external acid, so I write this below. And we have to compare number of moles of salt with number of moles of acid. Acid neutralizes external strong base. So let's calculate the number of moles. We didn't do that yet. We will find it by multiplication C and V. Okay, so for salt we have 35 milliliters and 0.2 molar concentration. So 0.2 multiplied 35 multiplied 10 power negative 3. This is a conversion to liters, and we got 7 multiplied 10 power minus 3. And for acid we will take 0.1 multiplied 25 milliliters. So here I put 10 power negative 3. And we will get, I think, 2.5 10 power minus 3. So this number is higher. And so it means that number of moles of salt is higher than number of moles of acid, and the buffer capacity by acid is higher than buffer capacity by base. Actually, that's it for today. I wish you good luck in preparation of home task. And the next question, we will solve problems on buffer systems of second time.